Our names for you, your names for us, so very sorry. Your surname is quite difficult to me. And so, multimodal machine learning, and I think, yes, floor is yours.
Thank you so much. Welcome everybody, thank you for coming so early to this talk. The talk will be about multimodal machine learning, as you can see. I will give a very short introduction about myself. End of last year, I finished my PhD in machine learning at the KU Leuven, it's a university in Belgium. It was about coupled data-driven models, so it will be very much like what I will teach you next about multimodal machine learning. After I did my PhD, I started as a researcher at Thomas More, more specifically researching in AI. So, like I said, I'm from Belgium. Belgium, a small country that you see here on the map. We're mostly known for our beer, waffles, fries, and chocolates. It's a very nice country, you should definitely visit sometime. And this is a photo of Mechelen, which is a city very close to our campus. So our campus, from Thomas More's campus in Nijmegen, that's where we work. We have a couple of bachelor applications there. We have automotive technology, electromechanics, mechanical design and production technology, and electronics ICT. So I'm from the Bachelor of Electronics ICT, and more specifically, I'm from the Applied AI track. So recently we started a track called Applied Artificial Intelligence in our Bachelor of Electronics ICT. A bit of an overview of what I will talk about. I will go shortly a bit into machine learning. Then I will talk about multimodal learning and a couple of the most important tasks there, which is multitask learning, multi-label learning, and multi-view learning. That's why my previous research was mostly about multi-view learning. You will see that the rest of the talk will be all about multi-view learning. I will talk about early net fusion a couple of times. I will show an example application and how we solved it. And I will also talk about some variations and I will do a conclusion at the end. So I will start about machine learning. So who really knows what machine learning is? Who has at least heard about machine learning? Raise your hand. Oh, I see a couple hands. Yeah. Okay, great. Who knows about neural networks? Yeah, I see a couple hands again. Okay, good. Neural networks, deep learning. Yeah, also. Kernel. Good.
Oh, they should.
And the kernel methods, like support vector machines, SVMs. Okay, that's great, that's okay. Machine learning, in short, where we have the classical models, which basically work with an if-then statement. So, example, if they want to differentiate between dogs and cats, they would go, okay, if it's small, if it has its nose hairs, then it would be a cat. Which works in some domains, but in others it really won't work. Like if you have pictures of dogs and cats, it would be very hard to do it. And it's also not how we learn. We know to differentiate between a cat and a dog because we have seen lots of cats and lots of dogs. And that's also what machine learning does. It learns from past experiences, or to talk about in computer terms, it learns from data. So neural networks, as most of you already know it, it's basically also based on our brain a little bit. We have these neural networks like this. We have inputs, so we have lots of pictures. Then it will go through these nodes. We call these blue ones the hidden layers. It's through all these connections, it can make lots of nonlinear combinations of functions. And then in the end, it will say, in this case, if it's a bird, a cat, or a dog. So this phase we'll call the training phase. Here we'll give lots of pictures to the network to learn. And then you have the inference phase where you give one picture, really a new picture that you haven't trained on. And the network will tell you if it's a bird, cat, or dog. In this case, it says it's a cat. Deep learning, also used it, yes. Deep learning basically brought a huge leap in accuracy. So where with traditional machine learning methods, the accuracy was going up and up little by little. It was going quite well, and suddenly we had this deep learning, and it was a huge leap. What's the idea there? The idea behind deep learning is that we have multiple layers. And it's also, again, kind of based on how we think. That every layer does like a part, like for example here, the first layer will kind of take the edges, then we'll take the combination edges, and we have like these objects already. So that's the idea. You have deep learning, and it really revolutionizes the machine learning field. Then I'll also tell a little bit about kernel methods. It's an alternative to neural networks, basically. The idea it's more based on statistical properties. So, for example, if you have a linear problem, you want to differentiate, you want to classify the red points and blue points. If it looks like this, it's very easy. You just have to find a linear line. You can do that with basic statistics. The problem is when it starts looking like this. So when you have to find it, you cannot find a linear line that groups the two different points together apart from each other. So you have to find a long linear line. That becomes a little bit more difficult with traditional statistics. The idea behind kernel methods is, okay, here it's difficult. Let's bring it to another higher dimension. And you can see here you can find a linear hyperplane to actually separate it. That's the basic idea of kernel methods. So then you bring it back and you get a nonlinear separation. You do that, you map them into a high dimensional space with a feature map. So yeah, instead of working in the space of X, you will work in the space of vacuum X. Of course, the problem is in finding this feature map, usually. And we will do that not by looking at the feature map on one specific point, but we will look at the feature maps of 2 points, and basically you have this kernel function which will actually look at the distance between 2 points always. And you have lots of options for this kernel function. So, multi-model machine learning, which is what the talk will actually be about. So actually a lot of real-life applications that you will need for your career. The data will actually be multi-model. So you will have heterogeneous data. So you have multiple submodels and you need to combine them. And that can happen in a lot of ways, and I will go into the most current ones. I will start with multitask learning. The idea is here that you want to learn multiple tasks, and instead of doing them all separately, you're trying to combine the models. Usually you're talking about related tasks, and since the tasks are related, it makes sense to do them together, because you have information from the other task that you can use. I'll give you a couple of examples. Say that you want to do image classification, and you have one problem where you want to differentiate between dogs and humans, and another task where you want to differentiate between boys and girls. The tasks are different. You could do that separately, but the tasks are also related. I mean, the information that you got here, you can only use here, and also information you have here, you can use there. So what you will do is learn them jointly to get a better performance. Another example here is, it's multitask learning in a language. So if you want to do some learning on a specific language, like if you want to classify documents or something, and you have to do that for multiple languages, usually those are multiple models, but also they are again related because you're always talking about languages. So it's usually better to do them together. And another example that you'll see a lot is about predicting drug combinations. And then for each drug combination, it's a specific task that you can do together. It might improve your performance. So this is like a schematic way to view multitask learning. So you have your features. They can be the same. Like if you think back about the example of dogs and cats, you have like images and dogs and cats are the same, or they can be different for each task. And then you have your model, which is shared by all the tasks. And then you have for every task, you'll have a prediction. So that's a bit schematic way to see multitask learning. An example, neural networks by itself are already multitask learners. So you can just do it with a normal neural network, where you can see each output can be a task. Like if you go back to a previous example, each task could be, is it the cat or not, is the dog or not, is the bird or not. And then these hidden units could be seen as a shared hidden units for all the tasks. So that's definitely possible, but sometimes it's not enough. Sometimes you have to do a little bit more. Sometimes you want to model a task relatedness. If you know how the tasks are related, we can also use that information to make a model better. This is what we call hard parameter sharing, because all the parameters, all the hidden units are shared to all the tasks. Another way is soft parameter sharing, where you have a different neural network for each task, but you're going to put some specific criteria on the node that they have to be close together, or something like that. And then you can also have a combination of shared hidden units and task-specific units, something like that. And then, of course, you also have task models which are based on kernel-based models or on Bayesian algorithms. Another multimodal paradigm is multi-label learning. So in this case, you don't have multiple tasks, but you have multiple labels. So if you look at the example here of a picture, we could label it mountain or forest or river. The idea is that an instance, so a picture in this case, can have 0, 1, or more labels. Again, some examples. If you have, I think it's from IMDb, but also on Netflix or something, you can have a movie and it can have multiple labels, like in this case, action, adventure, fantasy. Also, articles usually also can have a couple of labels of them. Or you can also see the hashtags on Instagram as labels. And there also usually you can have more than, you don't have none of them. It's actually a rather advanced task in machine learning. There's lots of research into it. Again, you have a straightforward way in neural networks to just, like each output, you make a combination. So if you have 3 labels, you can say first output is no labels, second output one label 1, third output label 2, and fourth output both labels. That will work as long as you don't have too many labels. Yes, I mean, if you have L unit labels, then you have 2 to the L outputs. And with your neural practices, can have a lot of labels, as you can see. And then this will not be feasible anymore. It will be too much. So also there you have some variations. Usually what you will do is you will model the label relatedness. So if you say you have pictures and the label sun and label beach will be closely related to each other, you can group them. That also group labels. And again, you have also different models and neural networks that can work with it quite well. Then you have multi-view learning, which is the thing that I was working with most. Here you will learn multiple representations or views jointly. So, for example, in the picture here, you have a dog, and you have literally multiple views from where you look at it. The idea is that the view will describe the same object in a different way. And you will also, again, try to learn them all together to explode information from all the views. So an example I usually give is here you have your model that wants to differentiate between a cat and a dog. You can just use a picture and have a model and try to differentiate. That might work very well. But maybe those pictures come from Instagram and you don't only have pictures, but you have also some hashtags. Like cats Instagram, cute, also here with the eyes. And instead of only using the picture, you might also use these hashtags. And then we can see the pictures as one view and the hashtags as another view. And then we can use multi-view learning to try to improve our learning. A couple other examples are if you want to, again, do image classification on the image and the caption. Or if you want to do some learning on social media, you can use the profile, but maybe also the friend list. Or web page classification, you can use the web page itself and the hyperlink. Or if you want to do some document classification, you can use the language, but also translations in other languages. If you want to schematically show it, it will look something like this. So you have for each view, you will have features. So in our example, these features might be the images, and here will be hashtags. You combine the models into one model, and you do a prediction. So when you saw it with the task and prediction for each task, now we have one prediction because we have one problem. If we look at all the three together, that multitask learning, multi-view learning, multi-label learning, the sub-problem are tasks, views, labels. We want to model task relatedness, view relatedness, label relatedness. The inputs are different, so multitask can have different inputs for the task, or they can be the same. Multi-view learning will have different features for each view, and multi-label learning have always the same features. And then the output's also a bit different. So multitask learning will have one output for each task, multi-view learning one output, and multi-label learning one output that can consist of 0, 1, or more labels. In all these cases, the submodels, or at least the information from the submodels, has to be fused together. And yes, the domain will focus mostly on multi-view. So, to go back to our overview, we have seen the most common multi-model paradigms, and we will go now a bit more in depth, mostly into the multi-view. One thing that's interesting to think about is the difference between early and late fusion. So like I said, we fuse information from the multiple submodels together, and there are commonly two ways to do it. You can do early fusion, so which means that you take one view and the other view, and you combine them, you get a combination of data, and then you learn them within the model. A typical example is feature concatenation, which just means you take a feature of this image, a long feature vector, you take the feature of this text, also again, probably a long feature vector, you just paste them after each other, and you learn on that. This is actually done a lot of times. The advantage is that the information is fused early on, so you can also exploit it early on. It's nice. The disadvantage is that all views are modeled the same way. You cannot put a different model for the image or for the text because you have combined data. The other extreme is late fusion. So here you will learn on your image, you have a model, then you will learn on your hashtags, you have a model, and then you combine the models. So that's the other extreme. We'll see an example of that later. This is an advantage that you are able to model them completely different, because you do them completely separate. But then disadvantage is that the information is only included in the very end. So you have modeled them completely different of each other, so you cannot use the information. So I said there are two types, but actually you will see that most multi-view methods will lie somewhere in between those. They will try to take advantage of both the early and the late fusion. So I will talk about some types of multi-view learning. They can be roughly divided into three categories, which are Concatenation learning, co-training, and regularization. So Concatenation, it's a very typical example of late fusion. This is really late fusion methods. So each view has a model. It can be neural network, it can be kernel-based, it can be anything, and it can also be different. So you can have total freedom there to model them all differently. And then you get a prediction. So let's say this view predicted 1, this view 2, this view 3, and then you take an average, get a final prediction that probably belongs to class 1. Okay, this might work already on simple problems, but you can also even make the simple problem, the simple learning scheme of Concatenation a little bit better by, instead of taking just the average, taking a weighted average. Like if you know that this model is actually a lot better, if you know it's more trustworthy, you can give it a higher weight. And with these weights, you take a weighted average, and then you say, okay, no, the class is probably 2. Sometimes these weights are inherently in the model already, because usually models don't just say, class 1 equals 2. A lot of times, you know the probability. Like they say, I think it's class 1 with probability of 52%. And like this model also, plus 1, 52%. This model says number plus 2, and I'm very sure 85%. So again, you take kind of like the weighted average, and you see, okay, now 60% plus 2. So that's already a smarter way to do cognitive learning, but still it's actually quite a simple model. It will work on simple problems very well, but if you go a little bit more difficult, it might not anymore. One of the earliest forms of multimedia learning, after the simpler ones, was co-training. So as you see, it's already an old method in AI terms, machine learning terms. The idea is that you maximize the agreement of two views on the unlabeled data. So the idea here is that you have some labeled data, but you definitely have a lot of unlabeled data. And you will try to make the two views, the models of the two views, align on these unlabeled data. And you will do that by learning them alternately. You will keep trying to improve it like this. I will explain it a bit better in the next slide. So it's mostly for either unsupervised learning or semi-supervised learning. And there are two major assumptions. So it assumes that each view already performs quite well. If you have a view that doesn't perform any good, it will totally screw up the algorithm. Then, this conditional independence, which means that if you have the labels, knowing what the label is in the one view will not help you in the other view. It's not that important. Here is actually a schematic way to see co-training. So what will happen? You have the unlabeled data. You have your classifier from the one view. So you actually make a model. Then you make a model from the other view. Classifier 2. And then you will let this model label some of the points of the first view. And this model labels some of the points of the second view. And then you start again. So this is, like I said, a bit in between those early and late fusion. Because it's kind of like late fusion, because you have a model for each view. But the information is also fused quite early on, because you keep doing this. You keep iterating over this. And the models will keep getting better and better and improve each other. Yeah, so that was the second way. Then the third way to do it is co-regularization. Here, so either neural networks or kernel methods, they usually try to optimize some objective function. Like in neural networks, is to minimize the error on the training labels. And the idea is that you take the objective function from one view and from the other. You just add them, and then you add a term that tries to maximize the alignment. It tries to make the views consistent. An example of that is multivariate least squares for vector machines. So, for vector machines is a kind of kernel method. So I'll explain it a little bit. It's similar to what you saw before. You have this problem where you have red dots and blue dots, and you want to classify them. You want to find a line. Okay, that's quite easy. It's statistics. Find a line that looks like this. The only problem here is that you have multiple options. There are lots of options here that will classify them quite well. You want to find the best one, which means that if you get a new point, it will classify it correctly. In sport vector machines, the best one is defined like this. So, of course, there are multiple ways, but here you'll do it like this. You will find the 2 points that are closest to each other, and then you put the line in the middle of them. And then, as you can see, so the line that you want, the separation line is the middle one. It's defined by this formula, and then you say this one, the red dot, this formula, and distance here is called the margin. Now that's just statistics. And then you say you want to actually maximize the margin, you want to make it as big as possible, which will be that you minimize the weights. And then you have a classifier, because then you can see, you take a line, and you can see, okay, if it's above the line and it's red, and if it's under the line it's blue. So you can take a sign and you know. So that's a very easy support vector machine for linear problems and for problems which are completely, you can completely separate. It gets a little bit more problematic if you have points that the data sets are not separable. If you would have a get point here, for example. So you basically say, okay, I allow for some misclassifications in the training. This will usually make your model better new points. It will look like this. So you say, I allow for some misclassifications. And then, of course, you don't only want to work on linear problems, you want to work on all problems, also nonlinear ones. So you're going to introduce this feature map that I said before. So again, we go to a higher dimensional space where we can do linear problems, and then we go back to work on all problems or nonlinear ones. So you're going to introduce this feature map that I said before. So again, we go to a higher dimensional space where we can do it linearly, and then we go back. So this is here with this feature map. So that's a simple support vector machine. It will always look like this. You have your objective function, you have some constraints, and then you have a classifier. Classify the points. Now this is support vector machines. Yes. Instead of calculating this, because that will be very hard, you will calculate this. So going from here to here, it's just optimization theory, but this is the same problem. Just hit in a different way. But this problem, it's a quadratic programming problem, and that we can actually solve a lot easier. So we'll solve this problem with the kernel function. So just a function that you choose to model the distance between the points. So this support vector machines, it's very old, but it's still used these days. It's pretty good. But even though a quadratic programming problem is easier to solve than this one, it's still not easy, it's still quite hard. So an alternative was found, it's called least square support vector machines. It's almost the same, but you have, basically the biggest difference is that you have an equality constraint here, and this is a dual model. So now the model that you actually compute looks like this, and that's just a linear problem that like every solver can solve this. So it's a lot easier, it's a lot faster to do it, and that's basically it. So the main thing that I want you to understand from all of this is that in kernel methods, in these square support vector machines, our model will look like this. We'll have an objective function, we have some constraints, we will go to the dual model with some optimization theory, and we get a linear problem that we can solve. That's the most important part. Then, so an example of this co-regularization is multi-view least square support vector machine classification. The learning task is classification, easy. So we want to, for example, classify cats and dogs. It's based on these least square support vector machines that we showed earlier. The idea is that we will integrate or fuse two of these models in a joint model, and then we will try to improve a classification. So this is might be a bit confusing, but it's actually quite easy. You just have twice the model that I showed you before. So you have the objective function of the first view, objective function of the second view, constraints of the first view, constraints of the second view, and then we have this coupling term. So that's actually the big key of it. So this objective term kind of couples our two views, and in here it tries to complement the arrows on the view. So it says if the arrow on one view is very high, that's fine as long as the arrow on the other view is very low. So it kind of enforces that. And yeah, it's just to show that again you get a linear problem. So again, it's easy to compute. So this model was tested on a couple of data sets. For example, on this data set where you had images, lots of images, and you had captions related to them. And then you had to try to classify these images into sports, aviation, and paintball. And then we had some findings with this. So here are a couple of examples. So the example contains always an image and a caption. And then you can see you have 2 different columns. These ones, if you would do them separately, so just use one model for the image, one model for the text, we're missed by the image views. So we're wrongly classified by the image views, which is understandable. If you can look at the first image, it should belong to class aviation, but it doesn't look at all like the other pictures in class aviation. Most pictures in class aviation are pictures of, well, planes. This one is very different, so it misclassified it as sport, but it's just difficult to do because it doesn't look like the other pictures. The other one as well, this belongs to class paintball, but it's a strategy board of paintball. It doesn't look like the other picture of paintball, so it was very hard to classify it based only on the picture. The other columns were misclassified by if you only use the text, which again is understandable. Here the text is simply timestamp. It's very hard to classify on that. And the other one is, it is related to the class sport, but it's very long. It has a lot of words, also some words that kind of align with the class aviation. It has some star and all these things. So it's very hard if you only use the text to classify it correctly. While all 4 of these images were wrongly classified if you only used one view, they were correctly classified if you used a combination. So this is basically to show that taking the combination of the views worked well. It did what we wanted it to do. I will now go to an example. So something that we actually worked on was weather forecasting. We all know weather forecasting. We all watch the weather channel or something, or look at on our phone. You want to know what temperature is tomorrow, for example. The state of the art, so what's used now also by Google and all these things, is numerical weather prediction. So that's a mathematical model. So it uses all the information that we have, all the physical information. It uses things like if the pressure is there, then it might rain, and like all these things. It's a very long mathematical model. It's very computationally intense. So it's hard to run. Recently, a lot of data-driven models have come up, which are basically machine models and which will use historical data. So which will look at all the data from all the weather stuff that happened before and try to predict it. So we want to have a model that predicts the temperature of tomorrow. Like if you have on our phone such a weather app, it will say the temperature of tomorrow. We want to have this. But okay, we need input for this model. And the input is basically weather information from the previous days. So in this case, we looked at temperature, humidity, wind speed, and visibility, but you can look at a lot more. So we used all of this from all the days before. You can go as far as you want, to predict the temperature of tomorrow. So that's nice. But you wanted to go a bit farther. Like usually on your app, again, you also have temperature of not only tomorrow, but also the day after, and the day after, the day after. So we also try to do that. So we also try to predict the day after tomorrow, the day after. We didn't only try to predict we tried to predict 2 temperatures. So the minimum temperature and the maximum temperature. Usually also, if you type it in Google, you see maximum temperature, minimum temperature. That's what we also try to do. We did some research into it, so we did a project with it, and we wanted to know the minimum and maximum temperature in Brussels. We lived in Belgium. We collected data from Weather Underground, which is the site where you can collect temperature data from all over the world. We used measurements for temperature, humidity, wind speed, all these things. We collected data not only from Brussels, but also from neighboring cities. Because, of course, the weather in Brussels is influenced by the weather in Brussels, but also by the weather in Amsterdam or different cities that influence weather. We wanted to predict the weather of tomorrow, but also up to 6 days ahead. And our data set is from 2007 to 2014. And then we wanted to test our model on 2 test sets, one November, December, so it's like winter weather, and one April, May, which is like spring weather. I don't know if you know anything about the weather in Belgium, but it's very hard to predict. Very difficult. And then we did it in a couple of fonts. So our model looked like this. You have information from all kinds of cities, from today, yesterday, the day before, and so on. You put it all in a model, and you get your prediction. Now, we immediately saw, okay, this looks kind of like multi-view learning. We can separate all this input data in a couple of views and try to improve our learning with that. So the first model that we did is we took each city as a view. So Brussels a view, Antwerp, Amsterdam, London. And then we used our multi-view method that you saw before, the multi-view least squares for vector machines, to predict the temperature. That already worked quite fine, but we also tried a different way, where instead of each city, each delay is a view. So the first view was the weather of today, the second view the weather of yesterday, so the day before. So that we also tried. So you can see, like I said, in a lot of real applications, we have multiple views. We have even multiple ways of dividing our views in this case. We could have done another way too, by the way. We could also do each view, like one view is temperature, one view is humidity. So there are still multiple ways to do this. And then, yeah, I want to show you some results. I just want to show you that also on a real, very tough problem, we can actually improve with these multi-view methods. So what you see here is predictions for minimum temperature and for maximum temperature. 1, 2, 3, 4, 5, 6 days ahead. And it shows the error in degrees of Celsius. So you can see the error only goes up to 2.5 in the highest. The blue one is weather underground. This is the state of the art. So this is this numerical problem. This is what Google will give you. If you ask to Google temperature of tomorrow, it will give you based on this model. So that one is very hard to beat. Then you have the yellow one, which is just the one view model. It just takes all the information, concatenates it, and uses that. And then we have the red one, which is our multi-view model. So it's error, so we want to make it as low as possible, obviously. You can see, here you can see that we are actually able to, for minimum temperature, we are definitely able to improve. We can improve on weather underground even very early on, and we also clearly improve on just using one view. This was a very nice example. And also maximum temperature we did very well. The only thing here is that you can see that weather underground is in the beginning much better, which actually makes sense because it doesn't only use machine learning, it also uses all these physical characteristics, so we expected it to be better. We were surprised by this result. But what you can see is that in the beginning it's better, but in the end we are actually able to improve it. So that's also what you probably noticed already. If you ask Google the temperature of tomorrow, it will do it quite well. If you ask it 6 days ahead, it might work less good. So we're actually able to improve there. So yeah, that was a very nice result, and we actually had it in our lab running for a couple months to so that we knew what the temperature was the next day. It was quite nice. So I told you about multimodal learning, I told you a bit more about multi-view learning, different types, I showed you an application, and then I'm going to go to a couple of variations that also exist. So I showed you the basic of multi-view learning. Like this is, if you see multi-view learning in literature, you will see it like this, but there are a lot of variations also. On one hand, you can have incomplete view data. So now we have all the data, very nice, but sometimes you have, in one view we have lots of data, and in another view there's some missing data because of some crashes or because simply people didn't collect it in all views. You have a lot of models that work on that. Large-scale learning, so if you have lots of data, you might know, if you know a bit about deep learning, actually deep learning is very good with that, so also obviously you have some multi-view deep learning methods. They also show nice results. Then you have semi and unpaired data, and pairwise versus simultaneous coupling. And I will basically explain those two a little bit. So paired, so to say paired versus unpaired. I will start with paired data. So far, everything you saw from Multimedia Learning was paired data. We had view 1, view 2, we had a point in view 1, and we knew the point in view 2 which it corresponded. So for each point, x in view 1, x in view 2, we knew that it represented the same sample, and so we knew that it belonged to the same class. That's fully paired Multimedia Learning, and that's how you will usually see it. But it's not always the case. Sometimes, again, because things were missing, or because you will need a special expert to actually couple them, and it's costly. So we might only have a couple of couplings. So we might have some points, like this point in this view and this point in that view, represent the same sample and will hence belong to the same class. But for the points, we don't have any information. That's called semi-paired data. Also, there's a lot of research going on. Usually, they use how close the points are related to each other, and then try to make couplings with points that are here related to each other. And then we have another extreme, where we don't know any couplings. So we don't know for this point whether it represents the same sample as this point. We don't know it for any. Now, if you have no information, well, then we cannot do multiple learning. Then you just have to do it separately, and you cannot do anything. But the idea is that we still have some information. We still have some information that this point and this point do belong to the same class. They might represent different samples. For example, this might be an image of a cat, and this might be hashtags belonging to an image of a cat, but a different image. So they do not represent the same sample, but they are in the same class. Or in this case, are a different class. That's also possible. And you can know it in between the views, but you can also know it in one view, like this point and this point belong to the same class, and this point do not belong to the same class. So you might have some information like this. We call them inter and intra-view constraints. The green ones are the must-link constraints, and the red ones the cannot-link constraints. So also with this kind of data, a lot of models have been proposed, and also you can see that only with a very small percentage of these constraints we can actually improve in using only one view quite fast, which is a very good result, because sometimes it's very costly to make these links, particularly it's a person that needs to do that. So we can show that even with a small amount of them, you can already improve a lot. Then for the next variation, I will have to show something with tensors. Who here has heard about tensors? No, it's okay, it's fine. I'll explain it for the rest. Yeah, I'm explaining it with an example. Imagine that you want to represent grades. So you want to represent grades on a machine learning course. And okay, you have the grade 89. Pretty good grade. That's really nice, but now say that you have multiple students and they all have a grade. You can represent it in an array, in this case, or what we will call a vector. So it's just for each person you have a grade. You can represent it like this. Now imagine that you don't only have for each person a grade, but you have for each person a grade in each year. Okay, you can still represent it by a matrix. Each row will be a different person, and the columns will be the year. Okay, easy to represent. But then, okay, it gets a little bit harder. We have a grade for each person, for each year, on each course. It gets a bit more difficult to represent it, and in this case we will use a cube. So for each person, for each year, and for each course, and we have a grade. So basically, what you can see is we will need a more dimensional structure each time if you want to represent something if you have another dimension. And basically, these are called tensors. So we call this a vector, we call a tensor of order 1, matrix will be a tensor of order 2, the cube will be a tensor of order 3, and we can basically go on and on and on. it's a bit harder to show. So a tensor is just a multidimensional object or array. That's it. So if we go back to our multi-view learning, we can look at pairwise versus simultaneous coupling. So what we did so far was pairwise coupling. So we looked at correlation between view 1 and view 2. We looked at correlation between view 1 and view 3, and view 2 and view 3. As you can, if you think back about the model, about the multi-view least squares support vector model, we had this coupling term. And you have a coupling term between view 1 and view 2, view 2 and view 3, like this. This can work quite well in most problems, but higher order correlations can be missed. So for example, if there is some information to be learned from the combination of view 1, view 2 and view 3, then you won't get it in these models. So the idea is here that we will work with tensors. So instead of only look at correlation between two views, we will look at the correlation between all views. So if we have more than 3 views, we will just have higher order of tensors. Yeah, to conclude. So as I said in the beginning, in a lot of applications, your data is inherently multimodal. You will see you can always spot either multi-view, multitask, multi-label, anything. There exist various multimodal learning schemes, and I basically explained the 3 most current ones. Most multimodal methods are a combination of this early and late fusion. It's usually good to do a combination, so you get advantages from both types. And the multi-view methods can be categorized roughly into 3 styles: the comedy styles, the co-training, and the co-regularization. So that was my presentation. You see, I finished quite early. So if there are any questions,
I have a question. When you try to build a model for weather forecast, as I see from your presentation, you usually use natural factors like factors that can be determined from the natural environment. But in Europe, commonly, we have a lot of, non-natural human factors that provide influence on weather. For example, in our region, we have a lot of pollution, not only from usual homes of people, but it should be also taken into account, but also big steel production plants, and they provide pollution of environment by heating, because they have big ovens and they produce a lot of heat. And it is not clear that work of this plant can be taken from the data, because the plant has own plan of work. And for example, if we will take into account only natural factors, maybe our prediction will contain more mistakes, because, for example, today this plant receive big order and they produce a lot of steel. They heat in a normal mode, etc. I recommend to use not only natural factors, but also try to select factors that may be human factors, but mostly important for this task, and also maybe you will have a lack of information, because by expert mode you can say, okay, there are a lot of factories, I will try to take from each factory information about volume of each day production or etc. But I think that it is hardly to measure such factors, and such weather model will be not so precise, because you will have a lot of your error, not as error of neural network or etc. method, but as error from these factors that you don't involve in your model.
Yeah, no, it's definitely true. The idea behind this, we've also thought about these things, not in that, it's quite interesting. But the idea was with us that these type of influences would also be visible in the historical data. So we only use indeed the natural data, but because it's historic, it's already influenced by these things. So in that way, it's in the model, but it might actually be interesting to try to put it also explicitly in the model. But as you say, then we need to have reliable data. But also, this is also a very good argument for data-driven modeling. Because, like I said, for us, it's already kind of in the data because it's in the historical data. But if you look at the numerical weather prediction model, the model that's used, that's really only based on the physics and on how everything relates, and that completely misses these kinds of things. So yeah, these things might be interesting to look at it also in regional, like to see how it influences. Could be cool too.
Thank you very much. Somebody else want to say some questions?
I need to ask how it could be applied into your diploma, masters, or bachelors. No ideas, no questions.
So thank you very much for your interesting presentation. From our organizers, I want to provide you a certificate of attendance of this school, and I hope that your visit to our university and our department will be a good opportunity to receive good impressions from this university, and also to provide us new knowledge. And I hope for your new visits and your participation in our events.
Thank you.
Thank you very much.